just want to show you one more bit that will help us speed it up even more. So again, I'm inside of the exercises sync directory, and I'm going to look at sync kernel.pyx. And a student suggested, instead of returning 1.0 here, to explicitly type the return value. So here we're going to say cdef double out, and I'm going to say out equals 1.0 here. And let's see here. Come on. There we go. Okay. So now we're adding a variable, a C double out to the body of our function, okay? And we just now have an if-else block, and the first path is when we're in that range when x is close to 0, and we set out to 1. The else clause, we use assign out to sign of x over x, okay? So let's try this and see if there's any difference. So Python test sync.py. There we go. So student claimed, so I mean it's within, I think, it's safely within just fluctuations in measuring time here, but it's still on par with solution time. But who is the person who says it? You got a much better result, right? Oh, I'm using a really old version of Cython. Wow, look at that. Eggs on my face. Well, let's see. Let me update Cython here.
Yeah, so when I run using that the test file, test sync C, I get up to 29 point something.
Oh, yeah? So much better than I got, huh? That's encouraging. Let's see.
And declaring it as cpdef gives a little slow.
Little slowdown. Okay. Well, I have about oh, jeez. So this is I have about 5 versions of Python installed. So I can always switch to a new one, a different one let's go to, I don't know, Canopy's Python. Okay, there's 19.1. Now let's try this again. Okay, one more time, Python. Well, I get pretty much the same. So I'm not sure. Let me pull up my code again, and you can tell me how mine is different from yours. Is this essentially what you have? Okay. And what's a performance boost you get over the Python?
Basically 23.8 down to 17.6.
So your per Python is 23 milliseconds.
No, with solution.
Oh, okay, I see. So you're like roughly factor 2 better than. Okay.
Oh, yeah.
Okay, interesting. Well, I'll have to look into that a little bit more. But bears pointing out that you can fiddle with what you're typing, and if you try to keep everything pure C just in the body of your function, like here, and just return a simple C argument, sometimes that can lead to a boost. Here it didn't hurt us at all. And some of this can be compiler dependent. I should mention as well that bears repeating that if you stick a docstring in here, Cython will put that in the appropriate place, and IPython will be able to pick that up. You can use question mark on it, that sort of thing. So, but it will not give you the argument signature by default. Like if you define just a pure Python function and then do function name question or function name question mark, you'll see the function signature. You'll see all the argument type, the variable names for the arguments, that sort of thing. You won't see that in Cython since that's in compiled code. So you have to repeat the function signature here if you want that information. Okay, but with that little extra bit, you can just stick that at the first line and then have the regular docstring information you would normally put in. And again, it just folds into the usual, like it just does what you would expect, okay? So why didn't I cdef double the function? Because if I cdef it here, let's try it. So now I'm going to run my test sync.py, and it gives me an attribute error because it can't find a cdef function. That's local only to that file. It's not exposed to Python. So it has to be either a def function or a cpdef function for that to be available to Python, external Python code. Okay. Okay. Any other questions? Take one or two more.
Just a quick correction. I was running the one in a different folder. So there's a C in the root folder, and for that one, the Python version is much slower.
I see.
I think that's
So
what
you're
it's
getting, I
using.
see, okay. Yeah, I apologize. I realized after the fact that my especially my Fibonacci, my fib directory is pretty messy because there's a lot of temporary stuff from when I was generating the material for this tutorial, and I forgot to clean it up before zipping it up for everyone. So that's leading to some errors. What I'll do is I'll clean it up and send it out a new version after this tutorial so everyone at least has a clean version. You can follow along with the slide material if you like.
Or if you just push this, the zip file contains the full GitHub repo with the upstream steps.
Okay.
If you push, you wouldn't just
That'll have already there, okay. Okay, so we've been using Cython keywords, that sort of thing. Cython defines cdef, cpdef, what else? Cimport, those are three new Cython keywords. And because of those new keywords, it makes it not valid Python. But Cython can just take a regular .py file and treat it like a pyx file, and that works. And there's a way to use Cython declarations that is still valid Python syntax and have a .py file be both just a regular Python file and a Cython file at the same time. Okay, and this is using what's known as pure Python mode in Cython. Okay. So on the left here we have our fib.pyx that we're sick of seeing by now. And we have our int n, which makes it invalid Python, and then our cdef int I, a, and b. Right? So let's say we want to have those same declarations to get the benefit of the speed up, but have it still be valid Python. Well, the way you do that is over here in fib.py, you import Cython, and now you give a decorator at cython.locals, and that's where you stick the argument signatures. In this case, n is a cython.int. And if you want, you can just stick, excuse me. If you want, you can stick all of both the arguments and the variables inside of that function body inside of at cython.locals if you want. Just stick them all in there, declare it all in one place, and you're done. Okay. I'm doing it just separate places to show you other ways of doing it. Inside of our function body here, we're doing cython.declare, And that's where we're declaring our A, B, and I. And it's fairly simple. You just treat it like it's a function, and the variable names are here, and you give it the types. So Cython.int, Cython.float, Cython. Double, whatever it is you're using. And the nice thing about this is that this is valid Python syntax, and if you run this as a Python file, if you say python fib.py, this will run and work, and all the Cython stuff is just completely ignored as if it never even existed. Okay, so it's just a no-op for the Cython stuff when it's running from pure Python mode. So you're gonna have a single file that now is kind of schizophrenic. It's kind of both Python and Cython at the same time, which is great. Now you still have to compile this either using pix-import or using setup.py distutils. We could stick this inside of a %% Cython IPython kernel, for example. Let's give that a try. So here I'm sticking in my pure Python code now, my pure Python mode stuff now. And let's give this a try. Oh, of course. One value to unpack. A, let's try that. Okay, there we go. So that worked. And let me change the name of this here. PP, so for pure Python mode, ppm fib. Okay, so now I have ppm fib of 3. Oops. So that works. And let's see, oops. Let me redefine my Cython version up here. Just want to show you that we do have the same performance. So here's my scifib is here. So that's my version using the Cython declarations. So I have scifib, I have ppm fib. Let's try those. Scifib of 3 and time it ppm fib of 3. So virtually identical performance. Okay. And if you were to look at the annotated HTML file that this spits out, you would see, in fact, that this there's a lot of white in here. Essentially, it's essentially generating the same code as if you statically declared this. Okay. Question?
You could modify your Python decorators. When would be a time that you want to do it?
Because, so the question is, why not just use this pure Python mode for everything? One reason is that it's a bit more verbose, right? You have to use a bit more stuff to make this work. The other reason is this doesn't, this works for simple stuff, but the Cython, using Cython code in a PYX file, you have access to absolutely everything that Cython provides for you. So this is a subset of what Cython allows you to do. And oftentimes it's enough, but if you want to do everything, like we'll see later on for the Capstone exercise, you need to put that in a PYX file. Okay.
So can you run this outside of
Yeah,
IPython?
sure. Let me just do this. Get rid of my %% Cython. So now IPython will say, do you want it outside of IPython?
That's
Oh, yeah, okay. Sure. So let's,
speed up was it much?
no, there's no speed up at all, but I'm just showing that the pure Python mode has the same performance as the Cython mode. So they're both fast. They're both faster than any, like if we were to do this in just regular Python without compiling it in Cython. So that was the reason for showing this. Okay, real quick, just going to show you this in oops. Okay, so here inside of, this may be one reason for people's pain with this fib example. Apologize. Inside of my demo fib directory, I have a fib.py file, which is the same contents as my slide here. So I'm just going to show you running that from Python. It's not going to do anything, but it'll at least show you that it's valid Python code. Didn't give us a syntax error or anything like that. And then I can say, let's do this. So import pyx import .ipython, pix import .install, and then I'm going to say import fib question mark. My bad. So that compiled my. Here, let me. Got to make sure I'm not compiling one of my other fib versions here. So I'm going to make a separate directory. Temp, I'm going to move my fib.py into temp. Okay, here, that's the only fib that I have. Okay, so there's no other way for me to work with any other fib. So IPython, I'm just going to say import fib. Okay. If I ask for fib, this is the fib, fib.py. If I say fib.file, it's just the fib in this directory. Okay, so we're absolutely sure we're using the right fib. Now, fib.fib of 3 is 5. Okay, so that works. And if you remember, this is mixed. This is our pulling in. It's importing Cython, but this is just a pure Python module. There's nothing Cython about this. Yeah. No, but you can use the Cython decorators inside of a pyx file if you like, and just keep it in that mode if you want. That's perfectly allowed, and that would have the same effect as if you use it. It doesn't matter if it's in a py file or a pyx file; it'll still work. So let me show you real quick now. I'm going to do the same thing, but except use pix import. And now if I say import fib dot, just fib question mark, my bad. This may not work. There is, there is a flag you can give to pix import to tell it to compile. Since this is a .py file, pix import just says, oh, it's a py file, just pull it in like normal. But you can tell pix import to compile even py files for you using Cython. So I'm not going to spend the time to look that up, but you can get this to work, okay? And you can get it to work just in pure Python, and you can get it to automatically compile for you and speed things up, okay? All right, so let's move on. All right, wrapping, the other main way of using Cython. And it's a lot of projects, the main part of the project is wrapping a major library like MPI, for example, in using Cython. So there are existing other wrapper tools like Swig, and Swig is a fantastic project. It's particularly useful when you have an enormous library to wrap. And with basically 5 lines of an interface file, Swig will slurp in that entire thing and wrap it for you automatically and give you something that will work from Python. It may not work nicely, but it'll work. And basically any function will have some interface that will work with other Swig functions that you've wrapped. You may not be able to inspect those things that those functions are returning, but it'll work. And that's the great benefit of something like Swig, because it's automating all this often tedious wrapping for you. The place where Swig becomes difficult, and I don't mean to pick on Swig, I'm just saying every wrapping tool has this problem where you need to customize the interface, and you need to be you want to take this really kind of clunky C interface that's just got a lot of work you have to do to just call a simple function, and you want to make it easier to use from Python. Well, you have to tell the wrapper tool how to generate that interface somehow. And the way Swig does that is by type maps. And if any of you has ever used type maps, you know they're quite difficult. They're not easy to use, and they're often error prone. I can never get them right the first time. And it's just difficult. Cython, again, it's I think conceptually easier, cleaner as far as what's going on, but it doesn't automate things to the same extent that Swig does for you. So you still have to do some work, but it's often worth it because the interface you can generate with Cython is often faster and nicer to use with somewhat less effort than you would use in another wrapping tool. Okay, but again, there are definitely use cases for Swig. I'm not going to say it's never use it, only use Cython for it. Okay, so it's up to you to evaluate which one's best. All right, so with that prelude out of the way, let's say we want to call the strlen function from string.h. Now, this again is just purely academic. This is all, yeah.
Just want to clarify on the previous thing. On all the inline declaration that we did with the Cython,
Mm-hmm.
with the fib.py, I included all the Cython locals and declare, and then I just go run that Python file. It should generate the pyx file for me, right?
It won't generate a pyx file for you. It will generate a C file for you. But the typical way to do it is to, let me show you this quickly. If I say Cython fib.py, I'm just calling the Cython tool directly, it spat out the fib.c for me. And then that needs to be compiled into an extension module. Okay. If we wanted to, we could have a setup.py file in here that uses the fib.py as if it were a pyx file, and it would all work. Okay. Okay, so back to wrapping. So let's say we want to wrap strlen from string.h in the C standard library. Again, this is purely academic. This already exists for us in Cython. Cython already wraps string.h because it already gives us pretty much all of the C standard library to use. But this is just a simple function to try out. So the way you do it is this one more new bit of syntax. Inside of a cdef extern from block, you give the signature for the function and other things that you're wrapping. So here, we're saying cdef extern from and then string.h, then a string. And there's a colon. And of course, you expect an indented block of code whenever you see a colon in Python or Python-like code. And inside of that block, you then declare all the things you're going to be using from string.h. Okay, this cdef does what you expect. It's declaring something as a C-level thing. Extern is saying this is some external thing that lives elsewhere, so don't expect it to be defined inside of this file. And then from string.h is saying what header file to pull in to include to make this, define these definitions. And then we declare here strlen, it returns an integer and it takes a car pointer, okay, so a C string as an argument. Now, the important thing to always remember is that the code that Cython generates for this block, no matter how many declarations are in it, you could have 1 or 1,000 things you're declaring from your header file here. The only code that Cython generates for this entire block is #include string.h. That's it. It does not automatically wrap string.h or strlen for you. It doesn't spit out anything that you declare. Okay? So why declare it? Well, the reason is we're telling Cython the argument types and the return type for strlen. So when we call it in other code, for instance down here in our getlen function, Cython can make sure that we're passing in the right arguments. We don't have incompatible types where we're passing in. We don't use the return type in an inappropriate way, that sort of thing. So we're just giving Cython type information about the function signatures that we're using from string.h here. That's it. Yep.
Could obviously lie about it.
Yes,
This one should be a problem.
it would.
Since that information's in string, you know why, what the design said, why not pull that information from string? First place, you don't want to avoid secret compilers.
That's right. Yeah, to do this in general is quite difficult because you need a preprocessor. There are projects out there that are starting to do this for us, to generate these declarations automatically. There is a project that's mostly in proof of concept mode called CRAP that does this. Essentially, it spits out these declarations for you. But it's a very good question, and people don't like Cython for this reason because you have to redeclare stuff, and that can be error prone if you're wrapping something that has interfaces that change, that kind of thing. But it's, this is a holdover from Pyrex. Yeah, it'd be fantastic if Cython came with a C preprocessor and it could parse a .h file for you automatically and extract this stuff. But again, I mentioned there are projects that are ramping up to do this sort of thing for you automatically. So I can't repeat it enough. The only code that's generated for this block, this cdef extern from, is a pound includes string.h. That's it. Doesn't matter what you declare in here. This only exists, these declarations only exist for the sake of the wrapper code that you write down here, okay, in the rest of your PYX file. So here we have a def function, getlen. It takes a car star as a message. This works with Python strings, by the way, so you can pass a Python string to this, and Cython extracts the appropriate pointer to the character buffer. And then inside of here, we just call strlen with this message as an argument, okay, and we get the integer back.
What happens if you pass a list instead of a car string or a string?
Let's give it a try. So copy that and stick it in here. Oh no, typo. Didn't like it. Nope, tabs and spaces. Oh, man.
Just use find replace.
I wish it were there. Okay, that works now. Okay, so just stuck that inside of a IPython cell with the %% Cython. Now we have getlen. Oops, let's see what that is. Tells us it's this getlen inside of this automatically generated Cython magic extension module. And so let's call it. So I call it with a Python string. Oops. Gives me back a number, right? As an aside, let's say I embed a null byte in here. Do you think the result of this is going to be 21 anymore? No. 10, right? Because if you know anything about C strings, they're null terminated. And so strlen just walks that string, that character pointer, until it finds a null byte and says, oh, I'm done. Python strings, of course, can have embedded nulls. They can have almost anything. The length of the string is separate from the string itself. So anyway, that's an aside. But it's good to keep in mind that you're working with C-level stuff now. But the question was about, let's call getlen with something else. The list, 1, 2, 3, 4. And you get a type error. Expected string or Unicode object list found. So it's going to make sure you can only pass in strings to this.
So you can't, like in C, you can do all sorts of crazy
Yeah, you
stuff.
can, exactly. You're not going to be able to do that here. But we'll see how to work with arrays in just a little bit. Okay, and then, again, to emphasize the point, possibly to beat a dead horse, but we declared strlen here. It does not wrap strlen for me anywhere. I can't say strlen anywhere. It doesn't exist. I'm going to get a name error, okay? So we have to wrap manually. We have to create a def function that wraps our strlen for us, and then we can call our def function or our cpdef function to make this work, okay?
So how did you get that % Cython to work?
This is just inside of IPython notebook, and you have to, before you use it, you have to %loadx Cython magic. Yeah, so if you're firing up IPython new, you have to do this %loadx Cython magic to use % Cython. Okay. So let's get a little bit more involved. Let's say we want to wrap the use some stuff from time.h, and let's say we want to create a function getDate that just returns the current date. Okay, so nothing fancy about it, but the interesting thing here is how little code you have to do to use to wrap, to call out to this non-trivial C library, because it's not trivial now because we're using a struct and we're have a very fluid mixture of Python and C here. So here again we have our cdef extern from time.h, and now we're declaring stuff that we're going to use from time.h. So if we want to use a struct that's inside of this header file, we say struct and then struct name : indented block of code, you just declare all of the things you're going to use inside of that struct. If you were to pull open time.h and look at the tm struct there, you would find, I think, 9 or 10 fields inside of that struct, but we're only declaring 3 here. So this is one way that we can be a bit nicer in Cython. You only have to declare the elements of a struct that you're going to use in your Cython code. Again, Cython doesn't generate any code from this entire block. It's just, we're just telling Cython the types of things that we're going to be using inside of this header file. So you can be as terse as you, I guess I should say, only declare what you're going to use. Don't declare absolutely everything, right? We only have to declare the functions we're going to use. Here we're saying there's a function local time. It returns a pointer to one of these tm structs, and it takes a pointer to a time t as an argument. And time t is a C type def, or a type def in C. In Cython you say C type def. That's another keyword. You don't have to. You're asking about whether you can do a type def struct or just a regular struct. Cython, it works either way. Yes, you could. Yeah, absolutely you could. Mm-hmm. So here's a type def. And again, we have a time function that takes a time t pointer and returns a time t as an argument. Okay, so we're just going to be using local time and time inside of our getDate wrapper function. So here's getDate. It declares a time t, and it declares a tm struct ts. Sorry, tm struct pointer ts. We call time with null. That gets the current time as a time t long as a result. Then we call local time with the address of that object. The address of operator works as you'd expect. And you get a ts. You get ts back, which again is a pointer to a tm struct. And lastly, I don't mean for this to be too tedious. I just want to show you working with a C-level library in Cython. Okay? So then we're just going to return now this thing. So first of all, what is it? Python-wise, what is this object? A tuple, right? But the contents of the tuple are built up out of what? The elements from the struct. So if you think about this, this is really quite amazing. On one line, we're building up a Python tuple out of the contents of a C struct, as if like it makes perfect sense. But if you were to look at the code you'd have to use to do this in C, it's ridiculous. It's nuts. It's crazy how much you have to do to just make this work in C. Cython is taking care of so much work for you here. It's just incredible. And this line is like worth, I think, tremendous amount as far as just what Cython is giving you. Okay. So you're reaching inside of the C struct, pulling out integers, and building up a Python tuple all at once out of this object and returning that tuple. Okay. So so that's our getDate. Let's try it out. I'll just do it in IPython notebook here. Hopefully I don't have any more indentation errors. Good. Okay, so stuck that in my Python notebook. That gives us a getDate function, let's call it. It's not too exciting as far as what it does, but we know that it's doing a lot of work for us. TM year 113. Believe that's years since 1900, so we need to add 1900 to that to get a reasonable value. There, that's better. Okay, so anyway, not too exciting, but it works, yep.
Where does it find the header file?
So when you're using a built-in header file that's part of the C standard library, you don't have to worry. It's just going to find it. If you've got your own, then you need to make, let's see, if it's in the current directory, it'll find it. Yeah, and that's a case where you'd want to use a setup.py file if it's in some non-standard location, because that's a place where you can specify, here are essentially, yeah, exactly. Essentially, it's a dash capital I on your command compile line. Okay. Not necessarily, no. There's an option to the extension class where you can say something like include dirs, and you give a list of include directories to look in. We'll see that in a little bit here, I think. All right, so that's basics on wrapping. We'll go into C++ wrapping here in a little bit, but I just want to take a side tour on extension types and Python classes. So here's a very simple class, particle. This is just a pure Python class. And I'm just bringing it up here to point out some differences between this and extension types, which you'll see on the next slide. So with a regular Python class, it inherits from some other type or object. And you can also use multiple inheritance, right? They're very flexible objects. And the important thing too is that Python classes are defined at runtime. I mean, Python, there's very little distinction between runtime and compile time. You almost always think of things just being compiled dynamically, and the Python classes are also very open to extension. You can stick a new function in there, you can tack a new attribute onto a object's dictionary, that sort of thing. Inside of the init, the argument here is a naked particle object, and its job is to assign it attributes so that it's now initialized. We just assign to self.m, self.vel, and self.pos or position. When you do these assignments, all Python does is it takes the right-hand side and it sticks it inside of the dictionary that's associated with this Python object, this particle object, right? That's all that's going on. So you can add a new attribute to an object outside of a class, for example, because it's just doing the same thing. The other thing is that since underneath this Python object, this particle object, there's a little dictionary. Again, dictionaries just hold keys that are Python objects and values which are Python objects. So there's really very little, actually almost nothing that it won't accept as an attribute, right? It's not going to be constraining the types whatsoever. We just happen to be passing m through float here to make sure that m is in fact a float when we call init, but we don't have to do that, right? Here's a method, apply impulse. It takes a force and a time, and it just does the kinematic equation for applying an impulse to a simple particle. And if we wanted to, we could have defined this apply impulse outside of the class and associate it with the particle class at runtime after the class is defined, right? So again, I'm just pointing out some of the main differences between Python classes and extension types, which this next slide has. So extension types are things like lists and dicts and sets and tuples, these built-in things that you work with all the time in Python. Strictly speaking, they're known as extension types or types in Python. They're very much like classes, and you almost always just treat them like classes, but you already know that there's several things they can't do. You can't say, if L is a list, you can't say L.A equals 10. We'll say, nope, can't do that. Let's try it out just to show you. So L is an empty list, and if I say L.A equals 10, attribute error, list object has no attribute A. So you can't assign, so types are closed to new attributes. They won't accept new attributes. The attributes that a list has are set at compile time, right? Same with dictionaries, same with sets, same with tuples, all these built-in types that you have. Same with their set of methods. You can't add a new method dynamically to a list. You'd have to subclass list, and then that's now a new open class that you can use. But the list type itself is not open to those sorts of things. And this is by design. Okay, question? No, it's still a type. And there's no particularly strong reason for doing so. Yeah, it was really just a habit of my fingers, basically. What else? If you know anything about how Python is implemented, these built-in types, list, dictionary, set, NumPy arrays are also types as well. They're implemented at the C level, and they have a C struct that holds all the data that's associated with this thing. And that C struct is not open to new attributes, obviously. C structs are very static, compile time, fixed objects, right? So, but they also have much better performance as a result. There's not this Python dictionary, you don't have this indirection to just look up the attribute of an object or look up a method on an object. So Cython gives us I should mention here, this class particle object. This is valid Cython code as well. And this will just give us a regular Python class that Cython compiles and it works, okay? When you create a cdef class, that's creating an extension type. And it's very much like a class, but it has these other things. It's not open to new attributes, it's not open to new methods, and it has much better performance as well when you're using attributes inside of this class. So here we have a cdef class particle, and this is creating a new type like list, dictionary, int, dict, that sort of thing. And then when you declare things at the top of the cdef class as cdef variables, these are the attributes that go inside of the struct for this extension type. Okay. So this defines the entire set of allowed attributes for this object. And they're put inside of a C struct, so it's a fixed sized thing. You can't add to it or remove from it at runtime. Cython, for these extension types, there's a special method called cinit. And cinit's job is to allocate and initialize any C-level stuff for this extension type when you create a new object of this extension type. So it's intentionally named like init. It's called at initialization time, but it's initializing the C-level stuff. So if you have, for instance, here, a float pointer vel and a float pointer pos for velocity and position, cinit's job is to allocate memory for those things, for example. So here we're calling malloc for vel and malloc for position. And I elided the checks to make sure that malloc didn't fail or anything, which is good practice, of course. But we're creating, allocating memory so that we can actually use these things later on, okay? So then down here, we're just initializing our vel and our pos, velocity and position, with the passed in sequences here, okay? I can have a cpdef function inside of the body of this extension type, and it does what you expect. It exposes it to Python level, and if you were to call this inside of other Cython code, it's going to call the C version of this method, okay? And lastly, there's a dalloc, under, dalloc, under, and its job is to undo whatever allocations cinit did. And this will be called by Cython for you automatically before this object is garbage collected. So since we malloced memory inside of cinit here, we have to free it inside of dalloc. So it takes care of the appropriate life cycle and makes sure we don't leak any memory. Okay. All right, so here's just a quick slide showing the difference between the two. On the top we have our Python class, and on the bottom we have the extension type version of that same class. So we're creating a particle instance, and vec is our just simple NumPy array that we're passing in. And we can access the velocity on this particle because, again, it's just the top level here is just our Python class. class, right? And vel is just an attribute. You can access it from outside. Python doesn't complain at all. You can apply impulse and look at the velocity again, see how it's been changed. And then outside of the class, we can add a new attribute charge to it if we like. Set that equal to 4.0. Down here now, in the bottom half of the slide, we have our extension type. And we call it the same way. It has the same interface. Takes a mass here, has to be convertible into a float, and then a position and a velocity here, okay? So created the same way, but we cannot look at the velocity by default, right? In part because the velocity is a pointer to a C float, which, or a C array of floats, I should say, and there's no way to directly translate that into Python, but also we didn't declare it as public. By default, all these attributes inside of our extension type are private. M here is public, is declared as public. There should be a type here, sorry. So cdef public float M. We can look at M, and since M is public, we can read from it, we can access it, and we can also assign to it if we like. We can call the cpdef method, apply impulse if we like. And lastly, we cannot assign new variables to this extension type. Okay? So those are the main differences between Python classes and extension types. Nice thing is that Cython gives us a very nice way of creating these extension types. And the big difference, of course, is that the reason why you want to use one of these extension types is because you have much more control about what's going on at the C level with these things, and you get much better performance as well. Okay. All right, so that's Cython working with classes and extension types. Now when we get into wrapping C++, this is when we want to start using extension types to wrap C++ classes. Okay, so that's why I brought it up previously. So here we have a very simple, oh my gosh, it's a holdover from a previous example. It should be called particle extern.h. Okay. So we have our interface. Everything's public here, so it's horrible C++ class design, but just for instruction reasons. Everything's private inside of a class. Cython can't get to it, so might as well not be there. It only cares about the public stuff. So here we have some public data, and then we have our constructor, destructor, that sort of thing. So very simple class interface. Here's how we wrap it in Cython. Okay, we use a cdef extern from particle extern.h. And we now say CPP class underscore particle, and then in quotes we say capital P particle. So what's going on there? Well, we're telling Cython that we're declaring a C++ class, and the underscore particle is the name we're going to refer to that class inside of our pyx file here. The particle in quotes is the name to generate for this thing inside of the generated source code. So the nice thing about this is you can give it a different name inside of your pyx file, and you can control the name that it uses in the generated code. So you'll see in the next slide here why you want to use this. So I'm sorry, there should be underscore particle as well. I apologize. So here you just declare all of the methods and the data that you're actually going to use that are inside of this C++ class. Okay. So this pyx file continues on the next slide. Here's where we actually wrap it. So we have a cdef class particle, and now inside of this guy we declare a pointer to one of these particle C++ objects. So cdef underscore particle star this pointer. Okay. It's a very common pattern you'll see in Cython wrapping code. So we're holding onto a pointer to a particle instance. We have our C init, and its job again is to initialize any C level stuff. And here now is where we create a new particle instance. We use the new keyword, and it's on the right-hand side. It looks just like we're declaring a C++ object. We'll go into what this is here in just a little bit. These float : one things, but it's just like an array. We assign that to our this pointer. Dialog deletes our this pointer, and that underneath the covers generates code that says literally delete self.this pointer inside of the C++ file. And lastly, here's apply impulse. We just pass that call directly through to self.thisPointer.apply impulse. Thank you. I'm sorry. Yes. So again, we just pass that call directly through to self.thisPointer.apply impulse. Even though this pointer is a pointer to a particle object, you still use dot notation. Cython generates the arrow for you in the generated code. Okay. All right. One last bit here. Cython supports properties. A little bit different syntax for declaring them, however. Again, this is inside of the body of our cdef class particle. And we say property mass colon. So the name of this property is mass. And we have a getter and a setter. So we define a get and a set. And all that does is pass through to our self.thisPointer.getMass. And then the set just passes through self.thisPointer.setMass. Okay. All right. So I realize I need to accelerate here a little bit. I apologize. In the interest of time, I'm going to be eliding our exercise here. But it's all there. So the one bit you have to change to make this work as far as compiling is you need to tell distutils that we're using we want you to use C++ to compile things rather than C. And you need to tell it that inside of the extension object here. Okay. All right.
Can you ever mix C and C++?
Certainly, yeah, you can, but you have to be careful. It's a bit bigger topic than I can get into here, but yeah, you can.
Could you call the get mass and set mass if they were private?
If they were private, no, you couldn't. Cython won't allow you to get to any private stuff. It's just like you, yeah, it's not going to be able to get around that at all.
So the only functions that you can do are just public.
Yeah, exactly. That's right.
The other file was a normal C++ header file, right? There's nothing special.
Correct.
And so you declare the get master actually public. Do I get an error then if I get to understand in the underscore?
Nope. You only implement what you need to use. That's it. And you only declare what you need to use inside of the cdef extern from block as well. So if you just want to wrap one function, one method inside of a C++ class, that's all you need to wrap. That's it. You don't have to redeclare everything. All right, so here's a very quick run through of using it. So we can create a new particle instance. Again, this is very similar to what we saw before when we were creating our own inside of Cython. This is wrapping a C++ particle class now. You can print the mass. You can assign to the mass. So again, mass is that property. When you print the mass, it calls the get on that property for you automatically. When you assign to it, you would call the set. You can call method apply impulse. And if you delete this particle object P, this is going to call the dialog for us, which underneath the covers calls delete, the C++ delete to clean up this C++ level object. Okay. All right. Slides on templated classes. Not going to go into it in the interest of time. Yeah. Question.
So you're showing things on the heap. Can you actually use stack-based boundaries?
You can. Yeah. I mean, for like scalar variables, if you declare them, right, they'll be stack based.
More like standard pointer, things like that. So
Yeah, you can. I did a project where they had their own reference counted pointer and did all that kind of stuff in Cython. Yeah, absolutely. And I don't have time to get into it, unfortunately, but you can deal with templated classes as well. And the way you do that is by sticking on in brackets the names for templated types here when you're declaring your classes in Cython, and then you use that capital T down here below. And then when you're actually using an object, you need to say underscore particle in brackets the templated type that you're going to use there. Okay, so instead of angle brackets, you use square brackets in Cython. Okay, so now this pointer is a pointer to a particle object with the templated type of float. Okay.
Why wouldn't you be using
I'm sorry, ask the question again.
Usually when we call templates, we call them source.
Oh, ignore my .h here. It could be HPP, right?
But could it be CPP as well?
Yes, it could. It's not particularly picky about what you name it at all. Okay, so all this is there inside of the demo directory. So if you care to look as far as like more fully worked example of this, I encourage you to go there.
I guess maybe I'll steal one question out of your templates to do a demo. Is there a plan to do a more nice way of doing many different template visualizations, or that's all you just use Ginger? And I'll be waiting for
So I wish I could say yes to that question. Right now, there's no particularly nice way. Yeah. So the question is, how do you deal with the fact that, like, if you're working just pure C++, right? The whole templating infrastructure kicks in and says, okay, you want for this templated class, you want to use floats and ints and doubles as the templated types. So it's going to generate that code for you and only what you need. But since Python proposes this difficulty with templated types where you have to pre-generate all the different types that you want to use because you don't know, right? It's dynamic and all runtime, so you don't know what other people are going to use beforehand. So you have to somehow basically duplicate this cdef class wrapper with the different template types and then provide some other layer on top of that to give a nicer interface for it. And I've given an example of it.
What about STL?
It's supported. I'll show right here is an example of pulling in vector from libcpp.vector. And it supports, you can do vector square bracket float, for example, and that's now a way of declaring a vector of floats in Cython. Okay. Fortunately, I don't have time to go into it here, but there is an example using that inside of the demo directory. Yeah, it doesn't. Boost isn't automatically supported, but you can use Boost. Yeah, you can absolutely use Boost if you need to. Okay, so a little bit more in C import. There's this. So let's say you're moving along. You've got one huge PYX file now that's wrapping all of your stuff, and you want to break it up into multiple things to have more like a library of Python or Cython source code. And of course, you don't want to duplicate code, so you want to have one PYX file use stuff from another PYX file. Well, Cython has another file type called PYD files, and this is where you stick the C definitions of things. And it's exactly analogous to C header files and .c files, implementation files. Right? The header files where you stick all the declarations, the signatures of functions, your struct definitions, that sort of stuff. And then your .c files implement those files and use stuff from header files. PYD files are like .h files, PYX files are like .c files. Okay, so it's the same analogous usage. All right, so over here we have particle.pyd now, and here we just declare the stuff we're going to be wrapping. We declare the signature of our extension types, that sort of thing. And then over here in some fictitious file, collisions.pyx, we say from particle, C import capital P particle. So that's looking for a file named particle.pyd, and it's pulling in the extension type particle from that thing. And now we can use particle as arguments to this function detect collision, okay? Yeah, it's valid Python code, absolutely. But the reason for this is this at compile time pulls everything together and compiles stuff together. If you were to do this, if this were just an import, it would still work, but it's doing it at runtime, so it's going to be slower. And it's not going to be able to infer, oh, this is an extension type, I can do the fast lookup on stuff rather than the slow Python lookup on things. Oh, no, this PYD is a Cython specific file extension. There is a Windows, unfortunately, very unfortunately, there's a PYD Windows extension for dynamic libraries. Yes. Yeah, unfortunately. Um,
You would use this in Linux, though, if you wanted to, right?
That's right. You would use it on Windows as well, but you just have to be careful that you don't have a compiled extension module that has extension PYD on Windows conflict with one of these things. Okay, so here are some examples. So Cython comes with several PYD files for you, okay? And the ones we've already seen are libc. There's a whole libc directory of PYD files. There's a libc.standardlib. And you can see import malloc and free from that, for example. It's very common. There's a numpy.pyd, which pulls in all the stuff from the NumPy C API. So if you ever need to drop down to the C level in NumPy, that's how you do it in Cython. This code right here is valid in pure Python or, no, sorry, this is not valid pure Python because we're using C import. Yeah. No. So what this is, if you look at the numpy.pyd that's shipped with Cython, this file just declares, essentially is a gigantic cdef extern from arrayObject.h, which is a header file that you always include whenever you're tapping into the C level of NumPy. And it's just declaring all the functions that you need to use from that C API. It's declaring the ND array struct that you would use to just use a NumPy array object in Cython, that sort of thing. That's all it's doing. It's just declaring those. Sorry, you know what? You're exactly right. This is written at a late time at night. It's PXD. Thank you. Very sorry. Thank you for correcting me on that. API? Versions of NumPy. Well, NumPy is fairly careful about API compatibility, but it is a good question. I've not run into an issue with it just because I've been using fairly recent versions of NumPy, but it's definitely worth keeping in mind. And I think Cython tells you which versions of NumPy that version of Cython is compatible with. All right, so here are some ones that are already given to us, libc.standardlib. Let's see here. And then lastly, it also wraps the most basic container objects from the C++ standard library. Okay, so vector, map, set. This line here. I'd have to take a look. In the interest of time, I have to move on. So I can take a look later, though. OK, now getting to the really interesting stuff for our Capstone exercise. All right, so I've used these things several times now. I want to talk about them in more detail. These are fairly new in Cython. They're called typed memory views, and they allow us to work with general buffers of data without making any copies. Okay, and these typed memory views allow efficient access to memory buffers without any Python overhead. NumPy arrays are included in this, but they're more general than that. And if anyone's familiar with it, they're using the PEP 3118 protocol. That is the general new buffer protocol for Python. So here's a very simple sum function, nothing fancy here. I'm just focusing on what's going on with the argument here. So sum takes a argument A, it's a double, and then in square brackets we have : : 1. So what's that's doing, this is declaring a typed memory view. The data type underneath it is double, and it's a one-dimensional C-contiguous buffer of doubles. That's all that we're saying here. It's one-dimensional because we don't have any commas inside of these square brackets, and the C-contiguous is the : 1 here. I mean, it looks a little funny, like we're slicing something, but this is the syntax you use for declaring a contiguous buffer. We're putting a 1 in the step slot, and that's like we're saying that we're not striding through this thing at all with a non-unitary stride. It's just a contiguous buffer of doubles. Okay. All right. So now we just have some simple declarations in here, and then we just walk through our array A and accumulate the values in S. Okay. Now we can compile this and use it just like NumPy. I wish I had time to show it to you, but we get basically the same performance out of this that we would out of NumPy's built-in sum function, okay? Yeah, question? It'll be a little bit slower, yeah. If you didn't have that, if I remove the last :1 and just had a colon here, that still works, it's totally valid. This is now a strided typed memory view. And the code that it generates when you index into this thing is a general stride calculation. So there's a little bit more calculation whenever you index into this guy, okay? So the ::1 says, assume this is contiguous, generate faster code as a result, okay? Then you would use, if it's not contiguous, if you pass in an array that's a view, that's not a contiguous array, you'll get a type error. Okay, so we'll see a little bit more on this next slide here. So here at the top, we're declaring inside of Cython code a memory view, type memory view, MV, and its data type is int, and it's a three-dimensional typed memory view now, right? Colon, comma, colon, comma, colon. This is very similar to anyone who's used Fortran 90 before, where you have the mention with colons in the slots, that sort of thing, right? All right, so here's our memory view. And then here we have 3 different A's that we're declaring. And we can assign this memory view to any one of these 3 different A's. This first A is a C declared static 3-dimensional array. Okay, so a C array, and you can assign MV to A, and that'll work. Okay? And again, these are memory views. They're viewing memory. They're not copying anything. They're just another way of viewing, of looking into a buffer of memory. Okay, that's all that's going on here. So it's very much conceptually similar to Python or NumPy views. Okay? Here A is just a regular NumPy array, and if you say MV equals A after this line, that'll work as well. That acquires a buffer that just looks into this NumPy array. And lastly, if B is another memory view, let's say here A is another memory view, and so you assign it to B. You can also say MV equals A here, and now A and MV, these 2 memory views, are both looking at B's memory somewhere. Okay, so there's 2 views into the same memory, whatever B's memory buffer is. Okay, you can index into them like you would expect, just like NumPy arrays. You get back whatever data type you declared here for the type, and you can use slicing just like NumPy, like you'd expect. If you use partial slicing, it's as if you stuck in colons for the unspecified dimensions, that sort of thing. Okay, so it's just like NumPy. You don't get back a NumPy view. You get back a memory view, a type memory view, but conceptually, it's very similar. Doesn't support fancy indexing. Just gives you basic indexing and slicing as a result. Okay. All right, a little bit more on type memory views. As far as how to declare them. This guy here, int with colons in the slots, is a strided memory view. So when it does the lookup, the code it generates is a general strided calculation. So it's assuming that there may be some non-unitary stride that it has to compute to get to any given location. So it's going to be a little bit slower, but it's more general. And you can give it basically any kind of NumPy array, and it'll work, even if it's a non-contiguous NumPy array. So here, for instance, we're assigning to strided MV this array, which is obviously not contiguous, no matter how an array started out as. Right?
How is the declaration different than the memory view in the previous slide?
I think it might be the same as the declaration previously. Yeah, it's the same declaration. I'm just focusing on what you can stick in the brackets now. Okay, down here now we have in the last slot, instead of a colon, we have a : :1. And what that says is this is a C contiguous typed memory view. It will not allow you to assign to anything that is not C contiguous in memory. Okay, so here you can assign C contig to MP.0s here, and that works. But if you try to assign C contig to this array, this NumPy array, that is not contiguous, C contiguous, you get a value error. Lastly, if you want a Fortran contiguous typed memory view, you stick a : :1 in the first slot. because Fortran continuity is contiguous in the first dimension, right? That's the dimension that varies the fastest. And you can assign to that a Fortran array from NumPy if you like, and that'll work. If you try to assign a C-contiguous array to this Fortran typed memory view, that will not work. You get a type error then. Okay. Wish I had more time to go into this, but I have to make time for our fairly large capstone exercise that pulls some of this together. Okay. All right. So, quick tour of type memory views. They're fairly easy to use. They work pretty much as you expect once you kind of understand how to declare them. Okay. All right. So our capstone exercise, we get to. This is becoming somewhat common now, computing the Mandelbrot set, the Julia set, that sort of thing. But it gives you very nice eye candy for. I like it a lot better than just saying, oh, it's sped up by 15%. Right. You just get a little scalar number in that case. This gives you a really nice visualization to play with. So. Let's see here. If you've fallen asleep, please wake up. Let's see, demo. We're going to exercises and Julia. And there's a lot here. Let's break it down. Let's look at the README. Actually, let's see here. So this exercise provides practice at writing a C extension module using Cython. The object is to take an existing Python module, Julia purepython.py, and speed it up by rewriting it in Cython. Okay. So the first step, the file Julia purepython.py calculates the Julia set in PurePython. To time it, run the following. Okay. So again, we're inside of, I'm inside of my zip file, exercises Julia, and you should be able to say Python timing.py and Julia purepython.py. Okay. So it'll take a number of seconds to run. It should pull up a matplotlib view visualization of the Julia set. And here it tells me it took 6.7 seconds to compute that. Again, we're just running in pure Python. Okay. So give you a chance to try that out. Hopefully it should work without issues. This is also just pure Python, so there should not be any issue. Okay. Now, there is a much more, well, before I get ahead of myself here, I want to go through what's going on quickly. So we have two functions inside of Julia purepython.py. There's a kernel, and there's a compute Julia function. Compute Julia takes two Python floats, CR and CI, n, which is the resolution, bound, which controls the domain in our complex plane that we're going to be computing over, and limit just controls the number of iterations that we're going to be using, or essentially controls the escape calculation. So Julia is a NumPy array. GridX and GridY are two other NumPy arrays. Julia is a 2D array that's going to hold our result. GridX and GridY are just allow us to iterate through our domain. C is a complex value that we declare here, and then we have a nested for loop. Right? This can be horribly slow Python code. You all know that because this sort of calculation in Python is just terribly slow. And for each location in our two-dimensional Julia array, we're calling our kernel function. And then when that's done, we just return that array. Okay. Now, our kernel takes in a complex number Z, complex number C, and a limit. Initializes count to 0, and it just has a while loop, checks the magnitude of our complex variable Z, and then it iterates. Z equals Z squared plus C, and increments count, and just checks to see if the size of our complex value has grown greater than limit. Okay? And this is just the core of the Julia set computation. It's very simple, and it's amazing that you get these incredible fractals as a result. So the result of this, is, what we're plotting here is the number of iterations, the count that it takes for that point in our complex plane to grow greater than a certain value. Okay, and for different values of C, that controls what this resulting Julia set looks like. Okay. So if you happen to pull open the timing.py, it just runs this compute Julia with a certain preset value of CR and CI. And I think N is like 200 or something. If you do timing.py-h, gives you a lot of information about the different arguments you can give. You can control these different variables. If you want to bump up the resolution, you can give a -n argument if you like. Okay. All right, so that's the basic timing stuff. What I want to show you is even more fun. You can say Python Julia UI.py and give it the Julia pure Python. This will pull up a GUI written in Chaco, what's now a interactive version of the same. Okay. This has nothing to do with Cython as far as the GUI is concerned, but it gives us an example of using something that's more like an application that you might use, right? So this is the intent of this is to give you something, okay, here's an existing application. I need to speed it up using Cython, right? Because this pure Python version, when I move these sliders, I'm modifying the real and imaginary components of my C variable, and it's changing the Julia set, but it's dog slow, right? So you want to speed that up, and using Cython here to get a more fluid experience. And this is still, I should mention that the sliders here are modifying the C value, the real and imaginary components of C. Down here, you can control the resolution with a slider, so you can click on that. This will probably take forever. And you can control the cutoff, so you control the number of iterations that it will bail on before it stops iterating. This is going to take forever, so I'm going to quit out of this. The pure Python version can't handle much, so you see the resolution is very grainy, that sort of thing. So a little bit more interactive way of getting feedback on how the performance of this is performing. I should mention in the lower left-hand corner, you don't see it on my display here, you should see a compute time displayed for each time it changes and recomputes a Julia set, it's telling you how much time it took to run. Okay. All right. So I should mention that if you're using Anaconda and you're on Mac, you need to run python.app instead of Python. So it needs to set up the windowing and the GUI stuff appropriately to make that work. So that's an aside. I believe if you're on Windows, I think it should work just fine out of the box on Windows. Again, so there's basically two ways of doing this exercise. You can just do the static way with matplotlib by running python timing.py and Julia, in this case, using Julia pure Python, and it just runs it once and gives you a matplotlib plot. So that'll work, that'll get the job done. All right, so now the actual exercise. Let's look at the README file again. Okay, so first step. We already did this, Python timing.py, Julia pure Python.py, and it gave us a plot, and it showed us the runtime for computing that plot. Step 2, bring up an interactive Julia set explorer. We run the following. And for those of you who are running Anaconda, you would run python.app if you're on Mac. Step 3, the pure Python version of the code has been copied into Julia Cython.pyx. You'll be modifying this file to get better runtime performance. To get a simple timing, please run the following from the command line or Windows command prompt. Okay, so let's try that. First, let's look at Julia Cython.pyx. And there's a bit more in here. It's essentially the same code, except instead of using complex values, we're now just splitting things out into two Python floats. That makes things just a little bit easier and gives us a little bit better performance. So now we have two functions, abs square. So this is the square of the absolute value for a complex number. That's what it returns. Here's our kernel. Same contents. We're doing the z squared plus c calculation explicitly now, rather than with two our real and imaginary components separate. But it's the same exact calculation as before. And here's compute Julia, okay? So your job is to take this file, well, first let's run it and see what difference we get in performance. So now I'm going to say Python timing.py Julia Cython.pyx. And this should detect that you gave it a pyx file as the argument and automatically compile that for you and run the code. Okay? It should. And I did my best to make sure this will work on Windows, to make sure it pulls in the right compiler flags, all that stuff. Okay? I mean, why is my version working? It is? Oh, man. You have default parameters and I don't? Oh, man. All right. So which file again? Julia.py? So when you call Julia Pure Python, what? Hold on. Why in the world? Are you using the zip file version of this, or are you using the GitHub version of this? The zip file?
So I'm using a demo version, and I call Python Julia UiPy and Julia Cython.py. It gives you this 6 arguments.
I see.